Hello everyone. So today I am going to share a very basic concept of how backpropagation functions. Basically, the backpropagation is a technique which is used in neural nets primarily to optimize the loss or the error of the model. So here we have this standard function of how we basically calculate the rate of change of a variable. So here a very simple example to have you guys explain it in very simple terms. So here we have variables a, b, c as 2, 5, 4, and d is a plus b and e is c into d, right? So you can also see the graph here, a and b, which sums it up to d, and then c and d, c into d is e, right? So what we want to do now is we want to see if we change any value, add any value to a, for example, how it would affect e, how much it would affect e, right? So we want to find two things. One is how much, by how much rate it would change. Second is we would also want to find the direction of change, right? So what we do here is to do that we will use this standard formula f of x plus h minus f of x by h, right? So h is nothing but here h is, for example, 1. We want to change a by 1, so add 1 into a, for example. So that's what we will do here. F of x is what we will define as e, okay, and then we just copy pasted this code here, and here we have f of x plus h, where we have the only change here is that we have added 1 into a. So we just got this answers or values here. So you can see after applying the formula, it is nothing but just taking the difference of e output, like without adding anything to it, and with adding a little bit to a, right? And we just normalize it by how much we have added it. So what we got here is 4. Now what does this mean, right? It means that the rate of change for e is 4 with respect to a if we add any small amount or any amount to a, right? Now you can, so now what we'll try to do is our goal is to find the gradient or the rate of change at each variable here, so that we can know the impact it will have on e. Now why do you need that, right? In backpropagation neural nets, it is very important to know this so that we can improve the loss. So here, for example, this is the loss, 28 is the loss or error, you can say, and we want to improve this error. Now we have to make some changes to this input values such that the error is reduced, right? So we need to know the rate of change at each point. For this, it is pretty straightforward that we can calculate the rate of change here, but in order to calculate the gradient is what we call that gradient for b and a, we cannot calculate it directly for e because we have to go through this d as well, right? So because this also affects e, so this is like an indirect gradient calculation that we need to do. So let's, instead of adding h or a little amount, h is nothing but it is just 1, right? So instead of adding it to a, let's add it to c, right? So if we just add it to c, and again calculate this, we'll get the gradient value as 7. So this is what the gradient value is for C. It's 7. As you can see, for E, the function is nothing but C into D. So when we want to calculate the derivative of C, derivative of E with respect to C, then we just take here 7, the value of D, because they are directly dependent here. But in case of A and B, it's a plus operation. So the derivative, so they're not directly dependent. It means that here, if I add any amount, it is going to directly, because this is a multiplier, it is going to directly impact how D is defined, right? So D becomes the gradient of C for E, right? So now what we'll try to do, instead of doing this, instead of going through again and again to get the gradient values of each variable, we will use chain rule. And what we do here is that we have dl. L is nothing but E, right? So we want to, our goal is to find the rate of change for each variable, so that our goal is to basically reduce the loss, right? So here dl by dd, that means that we want to find derivative of E with respect to D. So here we have d grad is equals to nothing but dl by de into de by dd, right? So here you can see that to calculate the gradient of D, we have to calculate the gradient of this multiplied by gradient of this. So gradient of E for E is nothing but 1, because if you add anything to E, then it's going to directly impact E, right? So it's going to be 1. And here the gradient of this, as I said, is going to be 4. So 1 into 4. For C, it's going to be 7, because D's value is 7, so it's going to go here. And then for B grad, now to calculate the rate of change, what I mean by that is, if I add anything here, what is the rate of change and the direction of change for E, right? So D of E with respect to B. Now in between D is what it comes. So what we are going to do is, we are just going to multiply the gradient of this multiplied by this, right? So that's what we did here. B grad is 4, that means the dl or E with respect to D is 4, and as you can see here, this is what we got. 4 into 1 is 4, so that's what came in here. And then the gradient of B dD with respect to B is 1, because it's an addition operation, so there is no dependency in between. So how much ever you add, it's going to impact directly, right? Because it's an addition operation. So that's why the derivative will be 1. So when we get this, it's going to be 4 for B gradient, right? And for A, similarly, it's going to be 4, the gradient of D, and the gradient of A, derivative of A, which is 1, right? As it's an addition operation. So this is how we got the gradient values for each of them. You can see the graph pointed here. For A and B, the gradient values are 4, 4. Here it's 7 and 4. It's the opposite values of each other. And then E, the gradient of itself is 1, because it's like direct attribution, right? So this is a good statement. I would like to also display what this is happening here is like recursion application of chain rule backwards to the computation graph. So we are computing the gradients backward, and why, and a question you would have is, why can't we calculate the gradients like this, the first way that I showed you, right? Like we just add a little bit to, for example, D here, let's do that. We add a little bit to D, right, and then we just calculate this again, we get 4. So why can't we just calculate the gradient like this? The problem with this is to calculate the gradient for each of the variable with for the loss, we have to again do a forward pass or like calculate these equations. Now in neural networks there are lots of neurons that it gets a lot of computation heavy, right, to calculate gradients like this. So this is how we do it in one shot. We do one forward pass, and then in the backward computation, when I say forward pass, it's nothing but just computing the final E, right, just going through this, right. So here it's going to be one shot because D grad, C grad and B grad, and they are just going to, I would say, sum up the effect, attribute the effect, right, backwards to the first variables. So that's all I wanted to share. Thank you for joining. There will be more videos like this. Thank you. Hi, one thing I wanted to add here is once we get these gradient values, we want to be, our goal is to reduce the error or the loss, right? So how we can do that now that we have gradient is that we want to change the input data such that we are going towards reducing the loss or going towards optimal state, right, or accurate state of the model. So there is a standard formula for that. What we do here, what's happening is here is that we have the value of a, right, as 2, and the gradient of a is 4. What does that mean is it's positively impacting the loss or the error. So when we increase the value of from 2 to 5, for example, as the gradient is positive, we will be increasing the error, which we don't want. So this formula, what it does is it's a minus 0.01 into 4. 4 is the a grad value, right, and 0.01 is the learning rate. It means how much big of a step or how much big of this change do we want to do to this data, right? And we are just going to subtract it from a, and we are going to get 1.96. 1.96 is the value, is smaller than 2 because we want to reduce E. Now if, for example, the gradient was, instead of 4, if it was -4, now what we would get, the new a value or the answer to this, instead of 1.96 we would get 2.04. It actually increased this data value because our gradient A tells us that it's negatively impacting the error. It means increasing this value will actually help decrease the error or reduce the error, right? So that's how this will be used at the end to update the input data, and again the forward pass that I told you will happen, and again we will change the gradients with the help of backward pass and then calculate and update the data. So this is all I wanted to add to this video. Yeah, sure. Thank you.